Hello.
Yep.
Yeah. All right.
Yeah, Shivdas, just one moment. I think
Sure.
I was just waiting for you, so I'm just beginning live stream. Okay.
You've started the live stream?
Not yet. I'm just. It usually takes a minute or two to log us in.
Okay. Am I audible?
Yes, you're audible. You're audible.
Okay. All right. So
it's not.
You started the live stream, Prasanna?
No, it's not allowing me to go live. Just a moment.
Okay. No problem.
It's taking longer than.
Can I ask?
I'm sorry.
Is my screen showing? Can I ask?
Yes.
Great. And is the transition between screens working?
Yes.
Yes.
Great. Good. Sometimes Keynote and Zoom don't work well together.
Yeah.
So Shivdas, maybe you can start recording it on your laptop or something, and then I can collect it from you in case live stream takes time.
No, my laptop is actually. I just finished one more meeting, right, with Akshaya.
No problem. I can record on my machine.
Yeah, it's very slow actually at the moment.
I see. Okay, I'll just take a minute more. If it doesn't work, then I'll just begin recording on my machine. Sure. I hope that's okay. Okay, thank you.
Yeah. So the YouTube live thing is not working at the moment?
Yeah, it's not allowing me to go live for some reason. It's supposed to activate, but it isn't.
All right.
So I'll just try once more, and if it doesn't, then I'll begin recording.
All right.
Yeah. Sorry about this delay.
That's good.
No worries.
Thanks. Oh, apparently the live stream has started. Okay, I didn't realize this. Sorry. So yes, it's ready.
Okay, great.
Okay, thank you.
So good evening, good afternoon, everyone, whichever applies to you. So today we have Dr. Peter Rohde amongst us, giving us this talk. So Dr. Peter Rohde is a senior lecturer in quantum software and engineering at the University of Technology, Sydney. He is a former ARC Future Fellow and author of the book, The Quantum Internet, published by Cambridge University Press. In his free time, he is a mountaineer, a rock climber, and general adrenaline junkie. So yeah, it's a pleasure to have him give us this talk. Over to you, Peter.
Great. Thank you very much, Shivdas. And thanks everyone for coming along and for the invitation to join you today. So as you've gathered, I'm going to talk about the quantum internet, the topic of my book from a couple of years ago. And what got me interested in this field was when I was working over in China with the group that probably many of you will be familiar with, because you'll have seen some of these pictures, no doubt, where they put up a low Earth orbit satellite that did entanglement distribution between, over 1,000 kilometers apart on the ground. And through that, they were able to demonstrate simple protocols like quantum key distribution, with the vision of working towards, in the longer term, some kind of satellite constellation network for quantum communications. So in this talk, what I want to talk about is what are the implications of this? Why do we want to do this? What's the reason to set up a quantum internet that distributes entanglement all around the world? It goes a lot deeper than just quantum key distribution, which is what's been done so far. So down here on the bottom right-hand corner, I've got the equation for what it is that this satellite does. It distributes entangled pairs where you have two photon states, one going in each direction, and their polarization entangled. So a superposition of one of them being horizontal, the other one being vertically polarized, or the other way around. And so that's equivalent to a Bell state when you consider polarization encoding. So I'm going to avoid mathematics because I don't actually know exactly who all the people in the audience are, but this is basically all we're going to make use of for now. The idea of a qubit shown at the top, which is a superposition of two logical basis states, 0 and 1, and a Bell pair, which is a maximally entangled state. And there are many ways you can make an entangled state, but I've used the example of 0, 0 plus 1, 1. Now, because we're dealing with photonics, when we're talking about a network, we're almost inevitably talking about optics, because we need moving qubits, not stationary ones. So we're going to use, for argument's sake, polarization encoding for all our qubits, where a 0 is encoded as a horizontally polarized photon and a 1 is encoded as a vertically polarized photon. So what is the quantum way to communicate information? In the regular internet, we basically distribute packets of information that can contain any information at all. In the quantum communication context, that's not so easy because of a phenomenon that many of you will have heard about called the no cloning theorem, which tells us that if we have an unknown qubit, and unknown is the important word here, if you have an unknown qubit, there is no possible quantum circuit or quantum operation that you can construct that makes two identical copies of that original qubit. Obviously, we can do that very easily with classical information. It can duplicate it all you want. And because classical information can be duplicated, we have a particular way of thinking about classical communications. We've developed this TCP/IP stack idea, where if packets get lost, the protocol takes care of it and retransmits it and keeps going until it succeeds. We can't do that with quantum information because of the no cloning theorem. And if we've got really valuable information in our qubits, something, for example, that's coming out of the output from a quantum computation, so it's encoding some really valuable information, we don't want it to get lost. And when we're encoding qubits into something minuscule, like a single photon, there's a good chance that it will get lost. So for quantum communication, we do things very differently. Instead of transmitting qubits directly, what we do is we communicate bell pairs, the 0, 0 plus 1, 1 here. Now, the advantage of communicating bell pairs is that they are not an unknown state, they're a known state, and therefore you can make as many copies of them as you want. So what we do is we use a sort of repeat until success strategy to distribute bell pairs between the end users that are trying to communicate quantum information. And then once we successfully ascertain that we have a bell pair between our two end nodes, we use quantum state teleportation to teleport our arbitrary unknown qubit via that channel that's mediated via the entangled pair. So the idea here is you take one half of the bell pair, you do a joint measurement on that, a maximally entangling measurement with the unknown qubit. You communicate only classical information and do some local corrections on the other side of the entangled pair. And then your qubit magically appears down there. And the important point here is that the only communication required is classical, so we don't have to worry about no cloning or anything like that. So by using the quantum state teleportation trick in combination with entanglement distribution, which is a distribution of a known state, we can completely bypass this whole problem of the no cloning theorem, meaning that if a qubit were lost, it's lost forever and we've lost all the information. So for the purposes of a quantum internet, that's what the goal is. The goal is to distribute bell pairs between end users. It's not to distribute arbitrary packets of data. So for all intents and purposes, think of a quantum communications network as just an entanglement distribution network. So what that means is that in such a future network, in the same way that bandwidth is sort of the commodity of classical communications, entanglement distribution is the commodity of a quantum network. All right, so how do we go about distributing entanglement? Well, the initial ideas on this were to use quantum repeater networks. Now, that satellite that I showed you on the first slide that was demonstrated in China, that was just very, very simple. It just directly sent out entangled pairs. But suppose we wanted to extend the range and extend the quality of that entanglement link, which is beyond the line of sight, for example, of a single satellite. Suppose we wanted to get round the world and go over the horizon. We're going to have to do it in segments. And quantum repeater networks do this. And they comprise two basic components. The first one is entanglement swapping, and the second one is entanglement purification. Now, with entanglement swapping, the idea is that if you take two bell pairs and then take 1/2 of each bell pair, so 1 qubit from each, and then do a maximally entangling measurement on those 2 qubits, what you're left with is those 2 other qubits now being left in a maximally entangled bell pair. So entanglement swapping can be used to extend the range of entanglement lengths. And we can just arbitrarily swap entanglement to extend the length. The other issue that we want to introduce is entanglement purification, because obviously the quality of the entanglement will deteriorate over distance. It'll be passing through whatever it might be, dephasing noise or depolarizing noise, some type of error channel. And entanglement purification lets us improve the quality of entanglement. And the idea is you take 2 low-quality bell pairs that have been subject to noise. You do a maximally entangling measurement on either of between 1/2 of each of them, and then you're left with 1 bell pair that has a higher fidelity than either of the original ones. Here I've drawn this circuit, how you can do this optically, where those square boxes with the lines, those are polarizing beam splitters, and they do bell projections, partial bell projections optically. So if you're doing this in the quantum circuit model, you would use CNOT gates there instead, but optically we can use polarizing beam splitters. And that experiment has been done, and we know that it works, so is entanglement swapping. Now, a quantum repeater combines both of these principles. Imagine we've got a whole bunch of segments going across horizontally, so a whole bunch of bell pairs. We do an alternating process of purifying down copies of bell pairs. So each time we do a purification, we halve the number of bell pairs we have, but improve their fidelity. And then we use entanglement swapping to extend the range of them. And we alternate between those processes until we end up with one entangled bell pair at the end that's of high quality and travels the full distance that those individual segments were not able to do on their own. So that's the basic principle of a quantum repeater network. And the important point of a quantum repeater network is that the success probability does not drop exponentially with distance. If you just send, say, a photon or any signal, say through the atmosphere or through an optical fiber, what you get is exponential attenuation. You have some number of decibels lost per meter, so that just exponentially accumulates. It turns out that these quantum repeater networks, by virtue of the order in which you go about doing the entanglement swapping, it doesn't have exponential decay, it has polynomial decay. And what that means is that you can get arbitrarily long distances efficiently without exponential resources. Okay, I did say earlier on that we're going to assume for all intents and purposes that that entanglement distribution is going to be optically mediated, and probably that will be the case. However, some pretty far out ideas have been suggested for how you can actually do this with stationary qubits as well. The reason for this is that entanglement doesn't suffer from latency. Every entangled pair is the same. It doesn't matter how long the entangled pair takes to get to a destination. All that matters is that it's there. This is unlike classical information. If you're making a phone call and you're sending the data along the phone signal, you need low latency, otherwise you can't have a phone conversation. With entanglement, that doesn't matter. So one thing that you can do to enable very, very high bandwidths, imagine we're looking at the future now where the requirements for building large-scale quantum computers are available to us. Imagine we're in that era. We can do everything we need for large-scale quantum computing, which means that we can construct a large-scale fault-tolerant error correction devices. And what we do with this idea of a quantum sneaker net is we take a whole bunch of bell pairs, an astronomical number of them, encode them into a fault-tolerant circuit, and then ship 1/2 of the entanglement over to the other side of the world or wherever it may be. So this is analogous to anyone who ever studied electrical or computer systems engineering. You might have heard your lecturer once say, what's the highest bandwidth you can classical bandwidth you can get? Is it optical fiber or is it satellite? The answer is actually it's a truckload full of DVDs that has way higher bandwidth than anything that an optical fiber can do, but it's not very useful to us because it has very, very high latency. But that doesn't apply in the context of entanglement on the basis that we're not transmitting the data itself, we're just transmitting this resource that's used for teleportation. So actually we can go back to that model. And so some colleagues of mine have done these calculations, and it turns out that this is actually a very viable high bandwidth way of going about achieving entanglement distribution, assuming we have the capability to implement large-scale fault-tolerant quantum computers. Okay, so I'll have a little bit of a chat to you about some work we've done on how we simulate quantum networks. So as we discussed before, I mean, the obvious thing that photons will be subject to is loss. If they're going through the atmosphere or optical fiber, there's going to be some chance of it getting lost. Similarly, it could be dephasing noise or depolarizing noise. Here on the right, I've written mathematically how you write these different types of error channels. So the loss channel, that equation has the interpretation that with some probability P, it gives you the state you expect. With some probability 1 minus P, the state is lost and you're left with the vacuum state. The dephasing state just has some probability of doing a phase flip on the qubit, and a depolarizing channel has some probability of replacing it completely with a mixed state. Okay, so imagine that we've got now a complex network like this one that I've got on the bottom left, where there are lots of ways of getting around. The vertices represent nodes in the network. This is where entanglement swapping and purification would take place. These are the active parts. And then the edges represent the channels, the quantum channels. And to get from one point in the network to another, we have to do some route finding. You can do this using shortest path algorithms. How do we go about modeling what's going to happen to entanglement as it passes through a network like that? So the way you can do this is you associate these channels like the E loss or E dephasing, E depolarizing with each of the edges. And then what we want to do, what you'll notice about these channels, the way I've expressed them, they're not additive, they're actually multiplicative. The chance of getting the original state back goes as p to the power of n as you apply that channel over and over again. We'd like to make this additive, because if we can make it additive, then if you go through a route through the network, you just add up the costs as you go, and it turns into a shortest path algorithm. Use Dijkstra's algorithm to find the most efficient way that minimizes loss from one point to another. And the way we can do that very easily is by just taking something that's multiplicative and turning it into log form. So if we've got an efficiency, for example, eta down on the bottom, normally eta is multiplicative. If we take the log form, it becomes additive. So now we've got channels that can be represented as additive costs, and we can use conventional route finding algorithms from classical networking theory to figure out what the optimal way of getting through it is. I've also introduced up the top here this idea of a multipath routing. Now, classically, you don't really do this, but with entanglement distribution, we can. What we can do is we can use multiple routes to simultaneously transmit bell pairs from one user to the next. And then at the end, we have multiple copies of the bell pairs, and we can use entanglement purification between them to end up collapsing it down to a single virtual link that's better than all of the other ones. That doesn't really have a classical analogy. So we developed a software package that we wrote about in this paper. You can look it up, and it's freely available on GitHub for experimenting with how quantum networks behave. This figure here is showing the behavior of quantum key distribution. What those colored numbers represent bandwidths as a function of efficiency and fidelity. So all of this can be easily simulated now. All right, so what do we do with this network? We know sort of what the underlying principles are for entanglement distribution. What are we going to do with it? Well, this is the one that no doubt you'll have all heard about, quantum key distribution, where you send randomized or photons in randomized bases, and the other party measures them in randomized bases. And then when you measure in the same bases, you keep those results. The one where you don't measure in the same bases, you throw those results away. And then you're guaranteed to have consistent outcomes. And if there's an interception, you can detect it. So this is a really old and well-known protocol. It's not really the long-term goal of quantum communication. The reason this gets so much attention is because it's kind of the only thing we can do with the technology we have, because it's such a simple protocol. So yes, this is what you'll read about in the papers because it's what we can do. But there are lots of other things we can do as well. Here are some more advanced things we can do. One is quantum enhanced telescopy. So you'll be familiar with these large baseline telescopes around the world, where they use multiple telescopes long distances apart. They link them together, and then they collectively create a virtual aperture as large as the distance those two telescopes are apart. They create a big virtual telescope, in principle the size of the Earth. Nonetheless, no matter how big you make it, you're limited by the resolution of classical optics. Now, if those telescopes, instead of sharing classical signals, shared quantum entanglement between them, that would allow quantum interferometric processes to actually enhance the resolution, the optical resolution you can get. So you could bypass optical resolution limits and achieve Heisenberg limits that are imposed by quantum mechanics. And there are people both here in Australia and all around the world doing research on this. How can we improve telescopy and imaging using entanglement distribution networks? Another one up here on the top right is quantum anonymous broadcasting. Here we're imagining that a whole bunch of parties share a GHZ state, not a bell pair, a GHZ state, which is the generalization of a bell pair to multiple parties. And what quantum anonymous broadcasting, or anonymous broadcasting in general, what it is a protocol where parties want to communicate. People want to be able to speak so that everybody in the broadcast can hear what's being said, but the anonymity of the person who's saying it should be ensured. So people can speak freely and openly, everybody can hear it, but nobody knows who's saying what. Now, classically, that can't be done perfectly. If you have a shared entanglement between the parties, there's a very simple protocol that lets you do this with perfect information theoretic security, meaning that there's no physical way in which it can be hacked. There are other things like quantum clock synchronization to allow more accurately synchronized clocks. You can have anonymous voting. There are a whole bunch of different cryptographic protocols, as I'm sure you'll gather by now. But the really interesting thing, the really long-term vision of a quantum internet is about quantum computing. The reason we have the classical internet is because we all have computers in our pockets and computers that plug into the socket that connects to the internet. If it weren't for computers, we wouldn't have the internet. And similarly, the really exciting thing about a quantum internet is, what does this mean for quantum computing? So the reason why quantum computing is so exciting in a networked context is because of the quantum phenomenon that, unlike classical compute power, which just accumulates additively, every time you add a new computer to the network, you're just adding on that amount of computational power to the network. But the collective power of the network is just the sum of the parts. Qubits don't behave like that. As I'm sure you all know, the power of a quantum computer, depending upon the algorithm that you're implementing, can in principle grow exponentially with the number of qubits. And what that means is that if you have a whole bunch of separate quantum computers and they're not networked, they behave additively as well. The collective power of all of them together is just the sum of the parts. But suppose you are able to network them together to act collectively as a single large quantum computer, then they would act as something far greater than the sum of the parts. And I'd like to explain how that comes about. And I'll show you how to do that in the context of the measurement-based model for quantum computing, which you may or may not be familiar with. I'm sure you're all familiar with the circuit-based model, which time flows from left to right and just your qubits go through gates in the way that classical computers do as well. The measurement-based model is different. What we do is we have a graph, which I've shown here on the right, where the vertices represent qubits that are initialized into the plus state, which is the 0 plus 1 superposition state. And the edges represent the application of controlled phase gates, CZ gates, between those qubits. And what you're left with then is a graph representing your state. And once you've prepared a lattice graph of a certain size, you can implement an arbitrary quantum computation up to a given size just by measuring out those qubits, not by performing any further gates, just purely by measuring the qubits in a particular order. The basis in which you measure the qubits is what determines the algorithm. Now, what dictates the size of the computation is the dimensions of this lattice. So the height of this lattice, if we're measuring out the qubits from left to right, the height of this lattice represents how many logical qubits are involved in your computation. And the width of the lattice going from left to right, that represents the circuit depth, how many gates you're able to implement. That's how you map the size of the computation back to the circuit model. So basically, a larger lattice represents a larger quantum computation. Okay, so consider this thing here that I've got drawn over on the right, this virtual cluster state. Here I've got a whole bunch of hosts, host 1, 2, 3, and 4, and each of those has their own little lattice cluster state, graph state, which in principle would allow them to implement small computations on their own. Now, suppose they were all linked up by quantum channels that allowed us to create links between those different lattices, and entanglement does allow us to do that. It turns out that that's exactly what entanglement does. It allows us to create a new edge between graph states. So if I've got these quantum channels connecting those hosts, I can sort of patchwork these small cluster states together to make a larger one, which has larger dimension than any of the individual ones, and therefore greater computational power, because it can execute a circuit with either more qubits or more gate depth or both, depending upon the dimensions of the underlying things. This is also a way you might think about building on a production scale quantum computers themselves, like I've got on the top left. You might imagine that we build small quantum computers that create small cluster states, and we mass produce them and link them up with optical fibers using this same patchworking idea. Similarly, down on the bottom left, you might imagine that entanglement is coming from a satellite. Imagine those blue entanglement links are coming down from a satellite, hitting two different ground stations, and they allow us to create this unified graph state, which is now geographically separate, geographically distributed. So this is really the idea of what the long-term vision of a quantum network is. And I'm sure you can see that this immediately has advantages that go beyond what classical networks do for classical computers. Okay, so to put this a little bit more precisely, here on the left, this is how distributed computation works in parallel. You might have like a root node. It assigns tasks, it assigns tasks to a whole bunch of other nodes. They perform their tasks, it comes back. You end up with a k-fold increase in performance, where k is the number of nodes. If we were doing a unified quantum computation, then imagine that each of those nodes had a number of qubits, n1, n2, n3, and you're running an algorithm that was growing exponentially with the number of qubits, exponential of n1, n2, or n3. You're not going to get, when you unify these together, you're not going to get the exponential of n1 plus the exponential of n2 plus the exponential of n3. What that unified computer has is the power exponential of, in brackets, n1 plus n2 plus all of the contributing qubits. And as you can see, that scales exponentially compared to linearly on the left. Okay, so now suppose we were to do that. There are going to be some security considerations here, right? Because the sorts of things that people will be doing with quantum computation are probably going to be quite high value things. It could be people cracking codes in the intelligence agencies, or it could be people doing some quantum simulation that yields some important intellectual property. So if we're going to be unifying the world's quantum computers, and you're going to outsource your computation to this quantum network, we're going to want to make sure that nobody is stealing all our data. And it turns out that there's a way to overcome this. There are two variations on this idea called blind quantum computing or homomorphic encryption. They're almost the same, but what they both provide is the ability to encrypt data, send it out to a quantum computer. The quantum computer executes an algorithm on the data without decrypting it first, sends the encrypted output back to you, which the client decrypts using their key. So neither an eavesdropper nor the server itself that's performing the computation is able to read the data, even though they're executing an algorithm on the data. Now, classically, this is not such a straightforward thing to do. It can be done, but it's not really practical for most intents and purposes because of the overheads associated with it. Quantum mechanically, it's much easier to do this. You can do it. Here I've shown how to do it optically. So here I'm imagining an optical circuit flowing from top to bottom. I'm representing qubits as a superposition of horizontal and vertical polarization. It goes through some unitary to give you an output state. So what we're going to do to encrypt it is apply the same polarization rotation, but a random one, to all of those qubits at the input. And then what you can see is that if you don't know what that polarization rotation was, what you're going to observe is a highly randomized state. But if you do know what that angle of rotation was, you can undo it at the end. And it turns out that polarization rotation commutes through linear optics networks. So if you apply a random polarization rotation at the input, you can undo it at the output. So the computer in the middle, or the eavesdropper in the middle that sees you, they see this highly randomized state. But a linear optics network will still implement the same computation. It's just in a randomized polarization, but you can undo that at the end. So this is a simple way to do it optically. You can do it in the circuit model as well, using this terrible sketch of mine. So consider the bottom left. Some of you might be familiar with the notion of a Clifford circuit. A Clifford circuit is one that contains, well, the definition of it, the Clifford group, is that it's the set of gates that when you commute Pauli operators through them, you get Pauli operators on the other side, not necessarily the same Pauli operators, but Pauli operators. And this Clifford group includes CNOT gates, CZ gates, Hadamard gates, all of the Pauli operators, Hadamard operations, basically almost everything you need for universal quantum computing except the T gate. And if you add the T gate to the Clifford group, then it becomes universal. But without the T gate, it's not universal. But nonetheless, I'm going to use the Clifford group for the purpose of illustration. So you can encrypt the Clifford group by exploiting this observation that Pauli operators applied before it is a different combination of Paulis after it. So someone wanting to encrypt their data on the left, down the bottom left here, they apply random Pauli operations to all of their qubits. And if you apply random Pauli operations to a qubit, but someone else doesn't know which Pauli operation you've applied, what they observe from their perspective is a depolarizing channel, which erases all quantum information. So the client knows what that Pauli is. And because it commutes through the Clifford circuit to give a different combination of Paulis, which is also easy to calculate, they can undo it at the end. But the person in the middle, they just see a completely depolarized state, completely mixed. So that's how you can perfectly homomorphically encrypt a Clifford circuit. And by perfect, I mean there is no mutual information that the computer or an eavesdropper is able to extract after you've done that Pauli encoding, because it's a perfect depolarizing channel. So you can now make this universal by adding T gates. That means that it's no longer Clifford, but you can get around that by using the notion of magic state injection. Instead of implementing T gates directly, you can use a particular input state in combination with a single qubit teleportation circuit, and that simulates a T gate. So there's a workaround for this. But this is the basic principle. The principle is that, as you can see upon inspection, there isn't a lot of overhead associated with this protocol. This is a very straightforward encryption and decryption process that perfectly obscures all information, but nonetheless allows a computation to be formed upon those qubits. Okay, so this is sort of the model that we're aiming for now, is cloud quantum computing. The server we can think of as being this big distributed quantum computer. It could comprise quantum computing nodes all around the world. They're all contributing together, acting collectively as something much greater than the sum of the parts. Some of the parts might be in America, some parts might be in China, some parts might be in India or Australia. And even if those countries don't trust each other, they can still outsource data to this collective distributed quantum computer with confidence, because they know that they've got information theoretic security in encrypting the data and outsourcing it using homomorphic encryption. So this is a very powerful model for commercialization of quantum computational resources, a much more powerful one than exists with classical outsourcing to classical supercomputers. If you're outsourcing stuff to classical supercomputers and it's valuable information, you need to trust the person who owns the supercomputer, which means, for example, that the American government might not outsource supercomputing projects to China, for example, strategic competitors, or the other way around. But with this sort of encryption, that ceases to be an issue. So here's a summary of what the advantages are of classical and quantum networking. So in the classical case, why do we outsource classical computing to the cloud? Well, there are a number of reasons. Firstly, it's to hedge risk through geographic diversification and redundancy. When you put something onto Amazon Web Services or something similar, you get a lot of control over, for example, geographic diversification, so that if, for example, a war broke out and a data center got blown up, everything is still safe because there's redundancy in different places all around the world. That's one of the reasons we use cloud computing. Another one is to maximize utility and efficiency. If everything is outsourced to servers, we can basically ensure that those services are operating at 100% CPU load the whole time, as opposed to if I do something on my own laptop, well, most of the time it's not doing anything. It's wasted compute power, so it makes it more efficient. And the other reason is it allows us to share assets. You might not have the money to buy a large computer, but you can still rent it. In the quantum case, all of those outcomes still apply. All of those advantages still apply, but some additional ones. There's collective enhancement in computational resources, meaning that if we all pool our resources together and then, for example, time share it between us, we all end up individually with much greater computational power than if we just used our computers on our own. That does not exist in the classical case. What this also means is that it incentivizes cooperation rather than competition. If there are all these different quantum computers all around the world, well, they're all going to be individually much better off from a computational perspective if they contribute to this pooled, unified quantum computer rather than just operating their quantum computer in isolation. So this is actually an incentive for global cooperation in the era where this technology is available. But it also does introduce some risks. So there is a lot of risk with becoming a client state where you're dependent upon outsourcing to others, because that can have strategic implications. It could cut you off. And that's something I want to talk a little bit about more now. You could imagine the following hypothetical scenario. This is a screenshot from my book. I don't know how it got published, but it did. So imagine the following hypothetical sequence of events. A Russian bedroom hacker with no direct access to quantum technology delegates a factoring algorithm used for cracking codes to the cloud and does it using homomorphic encryption. So he's in Russia, but the computation is physically executed on a server in the United States. The result is returned back to the Russian comrade, and he uses it to do something terrible against the United States. And the United States would have no idea because it was all encrypted. They wouldn't know what was being executed. So that's a very realistic scenario, and that has strategic implications because the sorts of things that quantum computing can provide does have strategic implications. We don't want to rent our quantum computer or contribute to a unified quantum computer if it means our adversaries are going to come back and whatever, crack our codes or steal our data, whatever the case may be. This is a fake tweet that didn't get accepted for publication, but it sort of sums up what would happen if Trump were president when this was the case. So here are the geostrategic implications of all of this. Firstly, leverage, the notion of leverage here. If two big players, say two big superpowers with similar quantum computational resources, were to unify their power and then equally timeshare that unified quantum computer, they would both get half of something much bigger than the sum of the parts, and it would be very fair. But if that was asymmetric, and one of those contributing partners to the network was contributing far more qubits than the other, and they were time sharing proportionately to their contribution to the network, what that means is that exponential gain would be tilted, would tilt things asymmetrically in favor of the larger contributor. So what this means is that if there's a lack of parity between strategic partners that are contributing to this unified network, it provides more leverage against smaller players than larger players. And what this means is that this could provide a diplomatic tool in the future. It could be an incentive, do us a diplomatic favor and, we'll let you join our quantum network. Or it could be used for gunboat diplomacy. And, if you don't do what you're told, we're going to exclude you from the network and you miss out on this pooled computational resource, and you'll just be left with that tiny little quantum computer that you have to use on its own, which is nothing compared to our big unified one. So there are lots of strategic considerations here, and the exponential nature of it really distorts the game theoretic foundations of how this quantum policy making might work, because a small asymmetry in the access to qubits can result in an exponential improvement in outcomes from a computational perspective. What this really means is that despite the fact that I said earlier that there's a strong incentive for everybody to collaborate and cooperate rather than compete, because by cooperating we get more than what we could get individually if we weren't participating in the network. But these geostrategic considerations that I've just mentioned, people not wanting these power to be used against us in an adversarial way, that could very well result in a fracturing of the global quantum network, whereby one superpower block decides to keep its quantum network separate from another superpower block rather than unifying them, because they're both terrified of what the other person might do if we were to unify it. So these will be important considerations in the future. It's a bit premature to think about it now, but these are definitely the sorts of things that will influence future quantum policy making. So to finish up, here's a little overview of how I think a future quantum ecosystem might look in the future. So down here in Australia, I've got a quantum computer there. It's connected by these red optical fibers to other nodes in other countries. It could also be connected by this brown boat, the SneakerNet, transmitting high bandwidths. Who cares about latency qubits? You could have China's quantum satellites distributing entanglement. These could all be simultaneously contributing entanglement bandwidth to the network in the same way that we have all of these different technologies contributing to classical bandwidth in our network. And they can all be consolidated, because the entanglement coming from all these different links using this multipath idea, they can then be purified down to create end-to-end entanglement links that have higher quality than any of the others. And I envisage a market for this, which I've drawn down on the bottom left is the upside down quantum NASDAQ. as I said at the beginning, entanglement is going to be the commodity of a quantum network in the future. Today, we pay for bits. When you buy an internet connection, you pay for a certain amount of bandwidth in bits. In the future, we're going to be not paying for transmission of qubits, we're going to be paying for entanglement distribution. We're paying a certain amount per bell pair between different points on the world. And so that's the nature of the economy that will underlie that, is an entanglement-based economy with a market where participants will be competing to provide the cheapest and best quality entanglement links, which then allows all of these exciting things that I've just mentioned. The other possibility, which is far more trivial, is that the economics of all of this don't work out at all. We just centralize it and put it in Antarctica because there it's nice and cool and we don't need to supercool the computers quite so much. So we don't really have much idea of what this technology is going to cost in the future. We know for certainty that quantum communications infrastructure is going to cost a hell of a lot more than classical communications infrastructure. How much more? That's really hard to know. Clearly, there's a big benefit in having a quantum communications network, but this is all emerging technology that hasn't been demonstrated on a large scale. This is in the lab at the moment. And in terms of mass producing and rolling this out in the way we do with present-day classical communications infrastructure, it's really hard to know what the price tag on that will be and whether these things will make sense. But we can only hope so, because the possibilities here are very exciting and there's clearly a very strong motive to do these things. This is my book. You don't have to buy it. I'm just putting it here for self-promotion. But this is the book that summarizes all of these ideas and a whole bunch of other things. You're welcome to have a look at it. And that's it. So maybe what I'll do now is I'll switch back to video mode. And if anybody would like to ask questions, you're more than welcome to.
Hi, so anybody has any questions for Peter? So I had a question, Peter. So there was this slide where you said that you were using, the noise was used in some sort of bandwidth or something, right? In one of the slides. So what do you imply by that?
Well, sorry, what did I imply by noise being bandwidth?
Yeah, something like that. I mean,
so the noise there, I was relating to how do you calculate what the total noise, what the best way of getting through a complex network from one point to another is. Normally, you would do that by saying, for example, let's ask how many dollars does it cost to use this transmission link, and how many dollars cost to use that one, and we assign those dollar costs to the edges and take the shortest path, and that tells us the cheapest way to communicate between two parties. So here we're doing things differently. We're calling costs not monetary dollars. I mean, it could be that as well, but we're associating cost with quantum channels. How much loss is there? How much depolarization is there? In other words, how much deterioration of the qubits is? Then you can use the shortest path algorithm and say, what's the best way to get a high quality noise bell pair that minimizes noise between any 2 points in the network. That's the idea of having these additive costs.
Right. Okay. Anybody else, Prasanna? Anybody else having any questions?
Yeah, hello. So thanks for a nice talk. So, you have talked about this multi-qubit entanglement and photonic distribution of photonic entanglement. So, could you see some application, or is it possible to have some fermionic entanglement distribution, because different eavesdropping attack like PNS thing will not be there in that kind of thing?
You can certainly have fermionic entanglement. Lots of solid state qubits would naturally be fermionic in nature, but so long as you can encode a qubit into it, at that level of abstraction, it doesn't matter what the underlying a two-level system is, whether it's bosonic or fermionic, what matters is you're able to encode qubits. And these arguments that are presented about security and the amount of entanglement, that's independent of what the physical encoding is. All that matters is at the end, you've got at the logical level a bell pair, and the choice of physical implementation is really irrelevant at that point.
Okay, thanks.
I had another question, Victor. What are the biggest challenges at the moment? Like, of course, like we don't have scalable quantum computers yet, and all that is fine. But like, what is the biggest challenge, otherwise, even theoretically speaking, in implementing a quantum internet?
Yeah. I mean, so this is really early stage development. Like, none of the things that I've talked about have been done at a large scale. So, for example, we can do entanglement swapping in the lab. We can do entanglement purification in the lab. If you want to convert that into a large-scale quantum repeater network, there are other technologies that you need to add to that. So I didn't mention, for example, that you'll need quantum memories. So when an entanglement link is shared, you need to store those qubits and wait until the next one to come before you do entanglement swapping, because those are both going to be lossy, right? So if they're coming from satellites, the loss through the atmosphere is astronomical. You lose almost everything. So you repeat until success, hold them in quantum memory. Repeat until success over the next one, hold it in quantum memory. And once you've got them stored in quantum memory successfully, then you do the entanglement swapping. So quantum memories have also been demonstrated in the lab, but all of this needs to be combined together. And these are astronomical engineering problems to unify quantum entanglement swapping, purification, quantum memories over long distances. Every individual one of these things is difficult on a long distance. Unifying them all together in a way that makes them compatible, working at the same optical frequencies, then interfacing them out to connect them to whatever's on the other side. All of these things haven't really even been demonstrated in a unified way, even in the lab, yet alone over long distance. It's very hard to know what the single biggest obstacle is, but I mean, ultimately the single biggest obstacle is loss. And that's why you need to repeat these things many, many times over and have quantum memories, which we don't really have. So there's no single answer to that question. There's a large conglomeration of individually hard problems.
Right, thank you. So just one more thing. When do you foresee, like, of course, I'm just generally asking this question, like, let's say even need not be a global one, but let's say within Australia or within Sydney, when do you foresee such a possibility? Like, how far from now?
Well, okay, so let's use China as an example, because they have quite an advanced network. I didn't show the figure of it, but there's a quite impressive figure that you'll find online if you look up China's QKD network. They've got an optical fiber backbone going down the east coast, intercepting a whole bunch of cities that have local area networks. Okay, but those are not a proper quantum internet. What they are is a trusted node quantum key distribution network. So you have entanglement between along every edge in that network that connects every node, but those nodes are only capable of measuring. They're not capable of doing swapping, purification, quantum memory. So actually it won't distribute entanglement across the length of China. It'll allow you to do trusted node quantum key distribution, but it's still a long way from being what I've described and being capable of doing the things that I'm doing. So yes, Australia is looking into building similar small-scale trusted node quantum networks. Lots of countries are. How long it will be until we have a large-scale network of the type I've described, where it's end-to-end entanglement links? Probably that will not happen, at least until well after the quantum computers are mainstream, because that's what would incentivize the creation of these networks, is when there are lots of quantum computers, people will say, hey, we should link these up because we're going to get a whole lot of compute power for free if we do. At the moment, there's no economic incentive to do this. We can build test nets for the purpose of demonstrating things like QKD for research purposes, but there's no economic motive to build a quantum internet when there's nothing to connect it to at the other side. I mean, the classical internet came a long time after classical computers, and you're going to have the same phenomenon, I would expect.
Right. So would it be possible with NIST devices itself instead of fault-tolerant devices?
Well, would it be possible with what?
And NIST devices, like let's say we have a huge network of NIST devices, but we're not into the fault-tolerant era yet, let's say.
Well, yeah, I mean, that's the thing. I mean, a NIST device, by definition, can't grow beyond a certain size. It just collapses because it's not error corrected. So if you wanted to unify them together, that's inevitably what would happen. If you took two of today's large NIST devices and connected them together, the whole thing would decohere and stop being useful at all. So it really necessarily implies, yes, we're in the era of fault-tolerant large-scale quantum computing to make this meaningful.
Right. Okay. All right. So anybody else has any other questions for Peter?
Yeah, I would have a question.
Yeah. Sure.
So when you say a quantum memory, you mean a quantum code, right? That's what you mean. To store
what I mean by a quantum memory is something where a qubit, say an optical qubit, comes in, it gets stored, then you can push a button and it gets released. So, for example, you might imagine that a photon comes in, couples with an atom, and that couples it to an electron energy level. And then using some process, you're able to stimulate the re-emission of that photon. That would be an example of a quantum memory. Just another way is to put a photon in a delay line in a fiber loop and just keep it running around in a low-loss fiber loop. That's a simple way to do a quantum memory as well. But all of these things are lossy and the coupling efficiencies are terrible. But there is a necessity just to hold qubits while we wait for others to come so that we can do things like entanglement swapping.
I see. Okay. Thank you.
Yeah, thank you.
All right. So if there are no other questions, let's thank Dr. Rohde again. Thanks, Peter, for giving us this wonderful talk. I hope everyone enjoyed it. Yeah, and we look forward to having more talks from you in the future.
Sure.
Thanks again. I hope
Thanks very much,
Is it okay to interrupt? I would just have one
sure.
last question, one
Sure.
final question. So when you do practical quantum cryptography, so what is the criteria to assess the rate? What does one capture practically when you're transmitting information from one person to the other or you're creating some kind of a key, say?
Yeah.
So what is it that you use to assess the performance?
So quantum key distribution, basically, what it does is it creates a secure random bit string between the two parties on the other side. And a classical random bit string. Now, there's a classical code called the one-time pad, which has perfect security, but it's very limited in applicability, which is why it's not used today, despite it being a classical code that cannot be cracked. And to do that code, all you do is you take your message bits and your key bits, and the key has to be the same length as the message, and you exclusive OR the matching bits together to create your ciphertext. And if you do that and you give someone the ciphertext, there's no way to figure out what the message was, because it could decrypt with an appropriate key to any message of that length. So that there's no information to extract other than the length. Now, the reason we don't do this in classical cryptography is because the limitation of the one-time pad is that not only does the key have to be as long as the message, meaning you need a large key, but you can't reuse the key. As soon as you reuse the key, the security is broken. So if you're trying to transmit a large file, well, you don't want to have a key that's gigabytes in size. You want a small, concise key. And that's why we use the classical codes that we do. So it's not really practical to share really large amounts of secure random bit strings between end users. It's much more practical to use public key cryptography on the internet. So QKD solves that problem by saying it gives us a way to create secure end-to-end random bit strings that we can then use for this one-time pad. That's what the goal is.
Okay, thank you. But I've been wondering what is how does one assess the performance? So you have a protocol, yeah. So do you talk about capacity? So what kind of measure does one practically look for?
You'd quantify it by the key rate, the rate at which you're able to use that quantum key distribution protocol to create shared secure bits between the end parties. So to give you an idea of what that rate is, that Chinese quantum satellite that I mentioned on the first slide, it's pumping out entangled pairs at a rate somewhere up around 100 megahertz, something like that. After the atmospheric attenuation, the rate of receiving those qubits on the ground, which then translate into shared secret classical bits once they're measured, ends up being at the level of hertz. So this is really slow. You can't hold a phone conversation if the bandwidth you need for the key is the same as the bandwidth for the message. Well, if the key is coming through at a rate of hertz, it's not very useful. So bandwidth is the biggest factor, and you just measure that by what's the rate at which I share classical bits.
Okay. Thank you very much.
Thank you.
Any other questions from anyone else? Professor Das, do you have any question? Would you like to say something to Peter? Okay, so if not, let's thank Peter. So Peter, like next time you come to India, do visit us as well, our center. That will be.
I'll try my best.
Yeah, okay.
Big country, I can't visit everything.
Yeah, I mean, I know of you visiting Bangalore very recently, I guess. That was last year. Was it last year?
Was it last year? No, I think it was the year before.
Oh, the year before.
Yeah. Mm-hmm.
Yeah, so yeah, if possible, do come to Kolkata and visit our center. That would be a pleasure.
That would be lovely. Thank you.
Yeah, exactly. All right. Thank you again. And